Welcome back, and in this video we're going to look at the last of the pure hydrocarbon series that we're going to look at, the last of those classes. We've looked at alkanes, which contain single bonds, alkenes, which contain double, and now we're going to look at alkynes, which contain a triple bond between two carbon atoms. As with before, we've seen that the alkanes have a general formula of CnH2n plus 2. The alkenes had a general formula of CnH2n straight because we've lost two hydrogens to make the double bond. And now alkynes, as I draw out the structures for these, have a think about it and see if you can figure out what the formula is going to be. As with our alkenes, we can't have an alkyne with only one carbon. So the first member of this homologous series is going to be ethyne, which is going to be C2H2, because we're going to have carbon with a triple bond. So each carbon now has 3 and 1 more hydrogen. So this gives us a CHCH in its semi-structural formula. Propyne, I'm now going to add another carbon in here to get 3. So I'm going to have C3, and then I'm going to have 4 hydrogens for this one because I'm going to put my triple bond, which must be linear, okay, because of the VSEPR structure of this one here, and then we're going to have a CH3 coming off here, and then an H coming off here. So we will have CH, C, CH3. Then we're going to continue our chain. Again, as with all things, I am drawing the one position isomer as we go through this. And I'm now at the point where I can increase my number of CH2 groups as I elongate the chain by just adding in the CH2 groups to each successive member. So we'd have C4, H6, C4H6, C5H8, C6H10, C7H12. This will of course be heptyne because it's 7 with the triple bond. We'll have CHC, CH2, 4, CH3. So we can see 1, 4 is 5, 6, 7 carbons. Things are going well. C8, H14, C9, H16, C10, H18. This will be octyne, non-9, and then decyne. We have CH, C, CH2, 5, CH3, CHC, CH2, 6, CH3. Again, we're increasing the number of CH2 groups between each successive member of the homologous series. Hopefully now that we've gone through all 10 of those, you can see that we've removed another 2 hydrogens because we've put in this additional bond between the carbons. That means that each carbon is unable to form a bond with a hydrogen. So we now end CnH2n minus 2 as the general formula for our alkynes. As I mentioned with the drawing of the structures of these, we do need to keep the C triple bond C linear. Okay, so when we do this, we will make sure that the groups that come off from the triple bond are linear, and this is because of the limited rotation and the fixed structure of this triple bond. So again, we will keep it linear through here. And then we bring back our zigzag. 1, 2, 3, 4, 1, 2, 3. And we can see here that we need to make sure that we don't add a hydrogen onto this carbon here, because that would give it 5 bonds, and carbon doesn't form 5 bonds, it only forms 2. Have a go at drawing out pentyne and hexyne yourself. Pause the video and then come back to see these structures. Well, hopefully your structures looked a bit like these, maybe hopefully a little bit neater than what mine do here, making sure that our bonds are nice and clear between which ones are connecting, and ensuring that you have 4 bonds only to each carbon. There's no 5 coordinate carbon bonds in there. We have our triple bond remaining linear, and making sure that we haven't added a hydrogen onto that one there. That's at the other end of the triple bond. Again, these are all the 1-ines. Okay, so I've drawn here but 1-ine, of course, and pent 1-ine, prop 1-ine, hex 1-ine are also included here. Remembering that we will have isomers of each of these, we can move the position of the triple bond. Okay, so if I was to draw but 2-ine, I would have 1, 2, triple bond here, and I would now put my CH3s at each end, and there would be no hydrogens on the central carbon. This would be but 2-ine as opposed to but 1-ine, which is this one here. Okay, so hopefully you remember how to name the alkanes, alkenes, and alkynes, remembering that we follow these steps. We identify the longest continuous chain of carbon atoms in a molecule, making sure to check that if our structure has been drawn around a corner, that we remember to count these ones as well, because they are still part of the chain. So here we would have the chain coming all the way up. Okay, so they need to be part of the continuous carbon chain. Find the longest number. Identify the type of binding. Is it single, in which case it gets the suffix -ane. Doubles, it gets the suffix -ene. If it has, and triples, it has the suffix -ine. Identify the side groups, so those branches, the alkyl groups, remembering that they can be classified as methyl, ethyl groups, depending on the number of carbons. Okay, so methyl will have 1 carbon, ethyl will have 2 carbons. Then number the carbon atoms from one end of the carbon chain to the other, making sure that we give the point of difference, be it the double bond or the branch, the lowest possible name, giving priority to the double or triple bond if it is there. Then we put it all together, remembering that each branch and the double bonds require a number to give the location on the chain where they are situated. If we have a look at this example here, first thing, we're going to identify the longest carbon chain, which will run through here. Okay, because if we went this way, if we went up this way, we can see it would be shorter. So here we had 1, 2, 3, 4, 5. Whereas if we go with the blue route, we have 6. 1, 2, 3, 4, 5, 6. So this is our 6 carbon chain. We have a point of difference here. Okay, so we're going to identify the longest carbon chain. I do believe this one is meant to be a CH3 if we look at the structure down here. So then we can identify the points of difference. We have 2 methyl groups hanging off. Okay, So then we want to number that gives the lowest combination. If I numbered from this end, 1, 2, 3, 4, 5, I would have 3 and 5. Whereas if I number from the right, going this way, 1, 2, 3, 4, I end up with a group on 2 and 4. So we're going to number from right to left in this case. Our branches are methyl. So I have a methyl group on carbon 2 and a methyl group on carbon 4. So I'm going to have 2, 4, commas between the numbers, dash, dimethyl, because this tells me there are 2 methyl groups, and then hexane, and it's ane because it's all single bonds. So now it's just a matter of practicing as many structures as we can draw using our alkanes, alkenes, and alkynes, drawing their isomers and naming them before we move on to the next functional groups.